Okay, as we discussed in goodness of fit test, we check whether the distribution of counts in one categorical variable matches the distribution given by a model. It can be a uniform distribution like a uniform distribution, or it can be distribution of another variable. Okay, and one thing we should notice is that goodness of fit tests are used to test hypotheses regarding the distribution of a variable based on a single population. Okay. Now, as we said at the beginning, there are three types of goodness of chi-square test, goodness of fit test, test of independence, and test of homogeneity. In case of goodness of fit test, we have one variable. For the others, for test of independence, okay, we use to determine whether there is an association between a row variable and a column variable in a contingency table constructed from sample data. Okay, instead of association, we can use words like, is there a relation between the variables, or are the variables dependent or independent? For instance, if we have like this data table, we may have a categorical variable showing the level of health, okay, against another categorical variable, and that shows the level of education. And for a random sample of 1670 residents, so here we have counts of data that fall into each category. For instance, here, out of 1670, 124 have an excellent level of health and some college degree. Okay. So the question that we test in test for independence is, does the sample evidence suggest that level of education and health are independent? At 0.05 significance level of significance. In chi-square test of independence, the null hypothesis can be expressed in different ways. It is important that it expresses a statement of indifference. For instance, we can say that the variables are independent. The variables are not related. There is no association between the variables. So all of them state an indifference. On the other hand, alternative hypothesis says that the variables are not independent, the opposite of null hypothesis. The variables are related. There is an association between the variables. Okay. Now the third group is test for homogeneity. In a chi-square test for homogeneity, we test whether different populations have the same distribution for a categorical variable. Now, instead of a single population as in goodness of fit test, we have more than one population, and we check if the distribution of a categorical variable is same, identical, homogeneous across the different populations. Okay, this is why it's called test for homogeneity. So the data can be viewed as counts for two or more groups on the same categorical variable. Here, for instance, we have leading CEO mentoring organization offers a program for chief executives, presidents, business owners, women and men executives that recently completed the program rated its value. So here are the perceptions of the program's value, the same for men and women. Okay, so is the distribution of the perceptions of the program's value homogeneous across man and woman. Okay. So in other words, is the proportion of man the same across all perception levels? So the null and alternative hypothesis for test of homogeneity are the distribution of the categorical variable is the same for all the groups versus the distribution of the categorical variable is not the same for all the groups or is different for at least one group. So here the same implies homogeneous. We can express null hypothesis and alternative hypothesis in a different way if we have two categories for the categorical variable, if it is binary. So if the proportion of responses in a category is equal for all groups. So if the proportions of man to woman is same for all the categories, for all the groups. Okay. It's same versus it is not same. When performing test for homogeneity and test for independence, we apply the same steps. Okay, mechanically, so they are mechanically equivalent. Okay, we calculate the same test statistic, we calculated the alpha value the same way. The only difference is the decision being made. The way we define the null hypothesis, and as a result, the way we make the conclusion is different. So, if we ask the question, are the groups or something like, are the groups are homogeneous? It is test for homogeneity. Yeah, but if we say, are the variables independent? This is test for independence. So, as in all chi-square tests, we calculate the expected count for each cell. Okay, for instance, here we calculate the expected counts for this cell. And how we calculate it roughly? We find the column sum for the column that this cell is in. Column total. Similarly, we add the values here, here, and here, and we get the row total. And the expected count, EI, is row total times column total divided by the table total. So all the values in the table. Sum of all the values in the table is table total. So roughly, we calculate the expected counts this way for both test for homogeneity and test for independence. Now, once we calculate the observed expected values using the formula, again we calculate the observed value of the test statistic. And it is the square deviation of observed values from the expected values divided by expected values summed over all the cells. Okay, and this distribution, this test statistics again follows a chi-square distribution. However, the degrees of this chi-square distribution is number of rows minus 1 times the number of columns minus 1. Okay. So if a significant difference between the actual counts and expected counts exists, which means that if the value of the chi-square statistic, observed chi-square statistics, is too large, then it shows an evidence against the null hypothesis. So for test of independence and test of homogeneity, we apply the same procedures, same assumptions, same test statistics. The only difference is the hypothesis that we define and the conclusions that we make based on this hypothesis.